Let's do another example of finding the complete factorization of a polynomial. And if you're wondering where to begin, I'd suggest starting exactly where we started in class this week, which is start by looking at your calculator and trying to find the real zeros. You can always start with the rational zeros theorem as well. Like in this case, I can see 4 is my constant, no leading term. So 1, 2, 4. I could start with the easy ones and see which ones work. But what I would probably do is start with my calculator, see what I can, look at all the behavior I possibly can about the polynomial before I begin, and that will at least get me started. So I'm just going to type it in, and this will save me the annoying process of randomly checking to see which ones work. And looking at the graph, it looks like maybe is that 2 is a 0. I can always trace to 2 and see if that works. It does look like 2 is a 0 of the polynomial. And notice since the polynomial doesn't pass through and actually turns around, that is most likely indicating that that polynomial has a multiplicity of 2 at that location. So let's go ahead and try that. So I can start with synthetic division. So I'm going to have 1, -4, 5, -4, 4. And synthetic division is the tool in which, advanced math, when we're studying polynomials more deeply, that is the tool for factoring, which is why it's so critical. And let's try 2. X minus 2 should be a factor. Hopefully, we'll find out if it's not. And it indeed is. And as the graph, kind of what I was saying about multiplicity, it can possibly be a factor more than once. Let's just try it again. You can sometimes have repeated zeros. And if I try it again, I'm going to get 2. Oops, 0 times 2 is not 2, 0. 1 times 2 is 2. And actually it is again. Excellent. So my conclusion is that g of x will factor as x minus 2 times x minus 2. And then the quotient 1, 0, 1 would be x squared plus 1. And notice when I arrive at x squared plus 1, this is sometimes what we refer to as a sum of squares, which again, going back to algebra, is something which is a prime. It can never be factored. Only difference of squares could be factored as x minus 1 times x minus 1. X plus 1 times x plus 1 does not work because the inner products would not cancel. But basically, if it says to find the complete factorization theorem, I should not be satisfied with this result, because what it says is that every polynomial can be completely factored into n individual roots. And since this polynomial was of degree 4, I should be able to find 4 of these things. And that's basically what the zeros theorem is saying, which is the next thing I wanted to cover. The zeros theorem states that every polynomial of degree n has exactly n zeros when taking multiplicity into consideration. And this is something that's really obvious from the complete factorization theorem, and it's a property that I kind of discussed at the very beginning when I was talking about graphs of polynomials, is that if it has degree 4, it could have up to 4 zeros. That's exactly synonymous to what this is saying, and why it's proved directly by the complete factorization theorem. And that was proved from the fundamental theorem, so you can kind of see how a lot of these ideas, to formally prove them, they're all hinged on this fundamental theorem. That's why, it's so important. But going back to this, we should not be satisfied because this should have 4 zeros. So far, I've only found 1 unique 0 with multiplicity 2. But this one, it's a quadratic, and every quadratic has a solution. Where I could use a quadratic formula, but actually an even easier way to do this one is I could set it equal to 0 and solve. If I subtract 1 from both sides, I get x squared is equal to -1. And applying the square root property, I'll get the square root of x squared is equal to the square root of -1. That is, of course, the imaginary unit. And then remember that when I take the square root of a square, this always has a potential of 2 solutions, plus or minus. In this case, the square root of -1 is I. So what I get is this quadratic has two solutions, as all quadratics must, unless specifically it could have, sometimes a quadratic could have a multiplicity of 2, have just one unique root. But again, by complete factorization theorem, every quadratic always has two answers. Sometimes they're repeated, sometimes they're weird, but it's got to always have two. And I found them here plus or minus I. And again, if I was to then factor the polynomial using them, I would have x minus 2. Again, I could write that as x minus 2 squared times x plus I, x minus I. And this would be the complete factorization of my polynomial. And again, I know it's complete because I see it has 4 factors. And also, if I were to list all the zeros, this polynomial has, well, c1 is equal to 2. I could say that c2 is equal to 2 as well, or I could just say that this root has a multiplicity of 2. And then it has another root, c3 is equal to I with multiplicity 1. And then c4 is negative I with a multiplicity of 1 as well. And this would give me the rest of my zeros. So that is the basically this leads me to my next theorem. I got momentarily distracted with what I wanted to say, but the next theorem is what we call the conjugate zeros theorem, which is something else that you might have noticed when looking at the last two answers. The conjugate zero theorem states that whenever a polynomial has a complex zero z is just a common letter that we use to describe complex numbers. So when I'm thinking of z, like I'm just thinking of a number a plus bi. That's when, just a variable that's commonly used in complex analysis. It says its complex conjugate z bar is also 0. So z bar, and I mentioned the term conjugate in the last couple of videos, that if I'm talking about a complex number, the complex conjugate is the same complex number with the opposite sign on the imaginary component. And often it's in complex analysis, we just write that as z bar, indicating a conjugate from z. But what the conjugate zeros theorem says is if one of them is a 0, its complex conjugate must also be. And if we go back and look at it, notice that in this polynomial, we had that the two complex zeros were plus and minus I. Those are conjugates of one another, and we can see that that's true. And if we go back to the previous example from the last video, notice that the two complex zeros we got, 3 plus 1/2 I, 3 minus 1/2 I, those were also conjugate zeros of one another, and that is not a coincidence. And you could go back and look at some of the other examples, but if a polynomial is going to have a complex zero, it has to have a second, the conjugate. And another conclusion from this is that conjugate zeros, they always come together in pairs, meaning that a polynomial can't have a single complex zero, it's always got to have two. And again, this is specifically only polynomials with real coefficients, just to be clear, and unfortunately, I wasn't very specific in the notes, which I regret, but it's too late to redo them now. And again, we're getting really into a lot of details. A lot of these things are not super important. If you're wondering, okay, we talked about a lot of crap. It's not crap. I'm just getting tired and being a little cavalier here. But if you see what I'm saying, we've talked about so much stuff. What of this is important? Well, what is important are the conclusions that we draw from these theorems. All polynomials can be factored, one big point. We can often factor them using these sort of weird numbers. Cool, but it works. Really the complex numbers are important. All polynomials can be factored. All polynomials have to have n zeros. That's another big conclusion. And if I do have one complex zero, it's got to have a second. They always are coming in pairs. And again, the reason why is just due to the nature of complex conjugates. Kind of like I was saying, when I multiply complex conjugates, they cancel out the inner products, and what I'm left with is only real numbers. And that's why the conjugate zeros theorem is true. Last but not least, the linear and quadratic factors theorem says that we can factor any polynomial with real coefficients into a product of linear and irreducible quadratic factors with real coefficients. But basically, since, and this is just another result of the conjugate zeros theorem, since complex zeros come in pairs based on, x minus 3 minus 1/2 I and x minus 3 plus 1/2 I, as we saw before, those always come in pairs. If you actually keep those together, those two form what we refer to as a prime quadratic. Like, basically, if I did not do the weird process of factoring in the previous example, what I would have had is a quadratic, which you can argue is a lot simpler than this. So it's sort of like the necessity to actually factor a quadratic using imaginary numbers. It's not necessarily that useful, and it's probably better just to leave it in the form of an irreducible quadratic, or prime. And when we say a polynomial is prime, we usually imply that it can't be factored using real numbers, and meaning we kind of just ignore the complex factorization. But basically, the reason why this last theorem is true is, and what it says is that all polynomials can be factored into linear and quadratic factors, is going back to the complete factorization theorem. Every polynomial can be completely factored. If I do have a complex zero, like I or minus I, those two have to come paired together. And if we simply don't factor them and leave them together, those form an irreducible quadratic. Kind of like in this example here, we were left with x squared plus 1. It's probably better just to leave it as an irreducible quadratic rather than factoring it using imaginary numbers. And just based on the complete factorization theorem, when I have imaginary ones, they come in pairs. All other ones are real anyways, and that's why this makes sense. I can fully factor polynomials into real pieces where when they're complex, we can leave them in the form of an irreducible quadratic. So that's going to wrap up the study of polynomial theorems. For those of you who made it all the way to here, congratulations. I know it's been a long road and there's been a lot going on in these lectures. And if you want to try practicing some more yourself, on the packet, there's 3 more polynomials. So what I'm going to challenge you to do is try to fully factor these polynomials using all of these various techniques. Start with a graph if you want, and go from there. See if you can find them all and apply these theorems. So like looking at them, this is degree 4. This has to have 4 zeros when you're taking multiplicity into consideration. Find all 4, identify their multiplicity. Same with number 2, it's got to have 5. See if you can find them all as a challenge. Anyways, see you all next time.